I'm Hermes. I'm a malware analyst at Tinexa Defense, as well as a PhD student at the University of Sagno.
Hi everyone, I'm Antonio. I'm a data scientist at Tinexa Defense, and I previously was a research fellow at the University of Sagno.
Today we're going to talk to you about network intrusion detection systems with machine learning. We'll see a couple of popular tools and approaches, and some of the bugs we discovered in existing tools. We'll also show you NetFlowMeter, which is our open source take on feature extraction. Then Antonio will show you the machine learning and data science side of it with data exploration with decision trees and autoencoders for anomaly detection. So why do we want to use neural networks for intrusion detection? Essentially, neural networks have really strong pattern recognition capabilities. So we want to use them to identify anomalies in traffic. In the state of the art, this also includes unknown attacks. That is, attacks that were not present in the dataset or maybe did not even exist at the time the model was trained. This is an actively research field, so you will see most of our references are academic in nature, but with this talk, we want to give you an overview of some of the common techniques and what results you can expect in the real world. An overview of the process looks like this. We have a data source, such as a pickup file, which is run through a software called a feature extractor. This will give us some features, which we can visualize them in a human-readable way as a CSV file. This is used as an input for a neural network to obtain a prediction, and this prediction is hopefully correct. The first hurdle we have to overcome is data collection. In practice, capturing complete network dumps is often infeasible, and nowadays, most data on the wire is also encrypted. What we do here is to look at the bigger picture. We aggregate packets into individual flows. A flow is a high-level representation of a connection, so it maps directly, for example, to a TCP connection, and it collects the metadata about this connection. Each flow has a number of metrics, which is what you see as columns in a CSV file. There are a number of well-known flow analyzers. The one we will be working with is CIC-FlowMeter, which is very popular in the academia. CIC-FlowMeter works mostly with numerical features, which is why it is very much used for machine learning purposes. Its features are network and time-based. So, for example, you may see features like the average of the delay between packet arrival. There are other solutions, such as OpenArgus and Zik. They are somewhat more popular in the industry because they work on application-level features. So, for example, if they collect a DNS packet, they can show you the human-readable query. Or if they collect a TLS handshake, they can show you the host name when the SNI is not encrypted. So this works better with rule-based solutions. So, as I said, we will be working with CIC-FlowMeter. It was initially released in 2018 alongside the CIC-IDS 2017 dataset. This dataset is very popular because it's widely used as a benchmark for machine learning models exactly for this purpose. CIC-FlowMeter was later analyzed and corrected by an independent group of researchers with this paper, which is called Error Prevalence in NADS datasets, where they found a number of issues both in the dataset and the tool itself, and released an updated version on GitHub, which kept on receiving updates until 2023. This updated version is the one we started our work. We used as a base for our work. So here are a couple of screenshots from Google Scholar showing the relevance of these search terms, even in the last year. Note that Scholar is not purely an academical search engine, so not of these are academic publications, but still it is quite relevant even today. So on this project, I worked on the automation of data collection and analysis pipelines. As we started scaling up, the AI team started reporting performance issues with certain pickup files. So we're talking below 1 GB of size. This is one of such errors. This looks odd because it's not a bug in the program, but rather it's coming from the Java virtual machine itself. It usually means we are running out of resources. Initially, we tried scaling up using better hardware, but it was clear it wouldn't work well. So we started looking into the source code to try and find the root cause of this issue, but code analysis revealed that the code base was too hard to maintain. It's a mix of C and Java, and it's clear it was worked on by a number of people throughout the years. Given also the overall lack of documentation on the code itself, we decided to work on a complete rewrite. This is what eventually became NetFlowMeter. which is a complete rewrite, and it's now available on GitHub under the MIT license. In particular, we worked on documenting and cleaning up the logic around packet processing and feature extraction. For us, at least at the start, we had a critical requirement that it had to be fully compatible on our dataset. That is, the output from our tool will have to be almost exactly the same as CIC-FlowMeter, so we could use it as a drop-in replacement. The biggest improvement we bring to the table is high performances. On average, we are 10 times faster, and on certain worst-case scenarios, we're up to 26 times faster. This 500 megabytes example here is a pickup file which contains many very short flows, which really hammer the garbage collector in CIC-FlowMeter. This is a nice improvement. However, it was not our goal. In fact, we achieved this result simply by using better data structures and linear complexity algorithms. If need be, there is still room for improvements, for example, by switching to multi-threaded processing. As for memory usage, we also see some improvement, but it's not as much as I would like. This is because we have to keep compatibility and emulate certain problematic metrics, which are the cumulative metrics. These are just a small number, but they require us to keep in memory all the previous flows, even after they're closed. This is an unfortunate legacy we need from CIC-FlowMeter to keep perfect compatibility. As a mitigation, we implement an optional feature which will break compatibility only on the specific subset of metrics, but which is able to reduce the memory usage to just 100 megabytes on a rolling input, that is, bigger pickup files or even real-time processing. Our development roadmap looks like this. Version 1 is already out on GitHub, and it's our baseline with CIC-FlowMeter compatibility. And throughout the rest of this talk, we will show you what we call version 2, which is currently in development, and it's more tuned for our use cases. Particularly, we will be dropping this compatibility requirement in order to fix a couple of bugs we'll see in a bit and implement some new features. We consider this version experimental because since we don't have a reference output anymore, it's somewhat, we kind of lack on regression testing. But if you want to play around with it early, most of the improvements are already documented in the code as to-do tasks. So you can already get the code and start hacking on it. The main improvement we are bringing is flow cutting. This is how we named a feature of CIC-FlowMeter, which always splits flow at in exactly 2 minutes chunk. This means that if you have a long TCP stream, in the output, it will show up as many 2 minutes flows. This is an issue because all of these flows have independent metrics, except for the cumulative ones we discussed before. We don't really know why this feature is a thing. We do have some hypotheses, but we couldn't find any definitive documentation. It is worth noting that this 2 minutes delay is not hard-coded. It's actually configurable. But to our knowledge, there are no major data sets that use a different value than the default. What we are doing here is that we are experimenting with removing this feature. As Antonio will show you later, the early results are promising, at least in certain cases. There are also a number of bugs we identified and fixed. Here I will show you a few. If you want a complete list, you will have to check out the code. This example here is related to the handling of the reset flag in TCP packets. What happens is that when the first packet of a TCP flow is a reset packet, CIC-FlowMeter will allocate the flow and never terminate it. You may think this is very unlikely, and in fact it is. However, it interacts with flow cutting. So what we've seen happen in our dataset is that we will get a reset packet after a natural timeout either on the client or the server, and this will just so happen to cross a 2 minutes boundary. This is much more common and triggers this bug. In the code snippet below, you see how we handle these issues in NetFlowMeter. So we usually leave a to-do task in the code explaining what's this bug, what it affects, and most importantly, how to fix it. But usually, as I said, for compatibility, we are currently reproducing these issues. Here is a more general issue, which is related to directional metrics. So CIC-FlowMeter defines a direction for each packet, that is client to server or server to client, and there are certain metrics that bind to this direction. The issue here is that the first packet handler will only initialize metrics in the same direction as the first packet itself. This becomes an issue for metrics which represent the smallest value we ever observed, and often these values are positive integer values. This means that in the output, we will see certain columns always filled with zeros.
Okay, so today I'd like to show you how you can explore your data to find common quality issues. And I'm going to do it using the CIC-IDS 2017 dataset that Hermes mentioned earlier. So why this dataset in particular? Well, first, it's a public network traffic dataset that was designed specifically for evaluating machine learning-based intrusion detection systems. Second, it's a widely used dataset as a benchmark in the literature. Third, both packet captures and labeled CSV files are provided. So obviously, we need the packet captures for generating flows using NetFlowMeter. And lastly, it's an interesting case study for data quality analysis as it has some known issues. So the data was captured over 5 days in July 2017, and only benign traffic is present on the first day, which is Monday. And then from Tuesday to Friday, there is a mixture of benign traffic and specific attack scenarios, like, for example, brute force, denial of service, or botnet activity. So the labeling from 2023 shows that the dataset is highly imbalanced, and this is a problem when applying machine learning, as it can lead to biased and misleading results. So here I listed some of the labels in the dataset and their frequency. And as you can clearly see, there are lots of benign port scan or denial of service flows, but just a few infiltration, cross-site scripting, SQL injection, or heartbeat flows. So for our purposes, we relabeled the data, and to do so, we referenced the updated labeling procedure from 2023. But we made some modifications for NetFlowMeter, of course, the version 2. So then we collapsed everything into 2 classes. So we only have the class called benign and attack. Then we also did some data cleaning, and we removed some rows containing infinite values. But actually, they were not present in NetFlowMeter, so we believe this is a problem or a bug in CIC FlowMeter. So in the table below, you can see that with NetFlowMeter, we get less flows, and this is due to the removed flow cutting logic. So now that our data is labeled, we can perform exploratory data analysis, and there are many tools and techniques to do so. However, today I'd like to focus on how you can use decision trees to gain insights into data quality issues and identify important features. So decision trees are a supervised learning method for both classification and regression, and they produce explainable rule-based trees. So here's an example. So basically, starting from the root of the tree, you evaluate some conditions on the features until you reach a leaf where you have your prediction. In our case, it's attack or benign. So let's build a simple binary decision tree classifier using the scikit-learn library. So I'm going to exclude some columns from training, like, for example, the flow identifier, source and destination IP addresses and ports, and timestamps. And I'm going to split the data into training and test sets using an 80-20 split. No data scaling is needed as decision trees are scale invariant. So let's start by setting a maximum depth of the tree of 5, which is already relatively small. So we can visualize the results on the test set using a confusion matrix. The confusion matrix is a table that shows us how well the model is performing by comparing the model predictions to the actual classes. On the main diagonal, you can see what the model got right, so your true positives and true negatives, while the other 2 boxes shows us what the model got wrong, so we have false positives, which correspond to false alerts, and false negatives, which are misses. So here is the performance we get for the CIC FlowMeter variant, and you can see it is already promising. And here's the performance we get with NetFlowMeter, which is slightly better. So now let's try lowering the maximum depth to 3. And the results on both test sets are still quite good. So this is starting to become strange. And of course, you can compute the importance of the features using a method like, for example, the permutation feature importance method. And you can see that the three most important features in both cases are the same. And it's weird that the first and the third one are related to TCP flags, in particular the reset and the push flags. So let's lower again the maximum depth to 2. And from now on, I'm going to show you only the results on NetFlowMeter for simplicity. So you can see that the performance is slightly decreased again. But this time we have a very small decision tree, so we can examine its textual representation. And we can see that basically we are first looking at this feature called reset flag count, which is the number of packets with the reset flag set. And since it's actually a non-negative integer, this means that we are basically checking if this feature is 0. And in this case, we look at the total connection flow time. And if its value is very short, then we predict an attack. On the other hand, if the reset flag count is greater than 0, then we look at the backwards push flags, where backwards indicates only packets sent by the server. So this is very strange, and we believe that here the class imbalance is likely affecting the results. So finally, let's set the maximum depth to 1. So this time we get a simple if-else rule on the reset flag count feature. And the performance, of course, is degraded, but not drastically. So this is weird. So basically, it appears that whenever a connection is not closed correctly or not in a clear way, then we predict an attack. However, something interesting happens if we only train using the data from Monday and Wednesday, which is our denial of service day. So this is mostly HTTP traffic. Then we get again an if-else rule on the second most important feature that we got before, which is the standard deviation of the length of packets from the server. But this time the performance is actually good. So if we look at the class-specific distributions for this feature, we can see a very clear separation. So this feature, we can say it's a strong discriminator between benign flows and denial of service attack traffic. So this prompted us to further investigate the data from Wednesday, as now Hermes will show us.
So when Antonio showed me this graph, we both thought it looked really weird. So I started investigating the actual pickup files provided by the dataset. What we see in Wireshark is that all the denial of service attacks look the same. They are a GET request to the root of the web server with a random query. And the server is always returning the same page. Investigating, it turned out that this is a default installation of the Apache web server, so it's always returning the same hello world page. I wanted to know how many requests are affected by this, so I identified this URL in the comments, which is a bug tracker URL, and used it as a marker. Searching this URL in the pickup reveals that almost every request looks like this. So what is happening here is that the model is not learning how to recognize an attack, but it's learning the shape of this specific request and response pattern. This means that even if the model we benchmark really well, it will transfer poorly to a different environment. As I was investigating the dataset, I also noticed another weird issue. This is the third line in one of the CSV files, and it has a weird-looking IP address. So I started searching it in the pickup files, and it revealed no results. What I did was going back to Wireshark and searched the binary representation of the IP address. This returned a single packet, which according to Wireshark is an ARP packet. Now, ARP is a network layer protocol. That is, it lives on the same level as the IP protocol. What is happening here is that we discovered a protocol confusion bug. That is, whenever CIC-flowmeter receives a packet that it doesn't know how to understand, it will always try to parse it as an IP packet. To confirm this, we can actually check the binary structure of an IP packet, and we see that at byte offset 12, we have the source address, which is the exact same offset where we find this byte pattern in the ARP packet. This is one of the bugs we do not reproduce in NetFlowMeter, because this only creates phantom flows which are not real data. However, it is interesting to note that as far as we know, nobody else noticed this issue in the dataset, despite it being literally as the third line in one of the CSV files provided by the dataset itself.
So now I'm going to show you a deep learning technique for intrusion detection that typically works well with data generated using NetFlowMeter. So this is a semi-supervised anomaly detection technique where we train exclusively on normal traffic. A classic model used for this purpose is the autoencoder. It is a neural network with a symmetric hourglass shape, and it mainly has two parts. So we have the encoder and the decoder. The encoder compresses the input into a lower dimensional representation in the bottleneck, which is our central layer in the net. And then the decoder takes this compressed representation and reconstructs the input. So we can exploit the reconstruction error that we get from this process, which is typically computed as the mean squared error for anomaly detection. So because the autoencoder was trained only on normal traffic, it will be very effective at compressing and reconstructing such traffic. However, it should struggle more with anomalies, since it has never seen them. Of course, to distinguish between low and high reconstruction errors, we need a threshold that we can compute in several ways. So what are the key advantages of this technique? Well, it doesn't require attacks for training. Keep in mind that anomalies are often rare, expensive, or even impossible to collect and label. So, for example, you can't collect attack data for every possible attack and configuration of existing tools. Also, this technique can identify unseen and novel threats. So, take the data from the results from Google Scholar with a pinch of salt, but basically there is a vast literature on this topic. So I'm going to use again CIC IDS 2017 as the reference dataset, specifically our NetFlowMeter version 2 variant. I'm going to train and validate the model on the data from Monday, which is our benign normal day. And I'm going to use an 80-20 split here. And I'm going to compute the threshold on the validation split as a high percentile of its reconstruction errors. In the end, I selected the 92nd percentile. So then I'm going to test on every other day, and I'm going to keep them separate to compare them. And I'm excluding the same columns as I did with the decision trees. And this time, I'm going to scale the data using min-max scaler from scikit-learn. So to build the model, I use the TensorFlow and Keras machine learning frameworks. And without getting into too much details, basically, I used a single densely connected layer of 56 units for both the encoder and the decoder. And then I used just 8 units for the bottleneck layer, which is also densely connected. And on the last line, you can see that the loss function is the mean squared error. So here are the results for Tuesday and Wednesday. So clearly, we have a very small false negative rate. However, sadly, there is a high false positive rate, reaching 10% on Wednesday. More or less the same is happening on Thursday and Friday. As a side note, you can visualize your reconstruction errors on a diagram like this one. I place the reconstruction error on the y-axis and the index in the errors array on the x-axis. And I'm using a semi-logarithmic scale. And as you can see, for example, this is useful for debugging or further investigating your results. For example, if you see an attack point under the threshold, that is your false negative. So let's try something now. What happens if we only put 1 unit in the bottleneck layer? Well, the results are bad, except on Wednesday. where they are very similar to the previous results. We believe this is due to data redundancy as discussed. So let's try something else. What happens if we restore the flow cutting behavior of NetFlowMeter? We have an experimental feature in the version 2 to do just that. The performance drops significantly, specifically on Thursday and Friday. So here you can see the comparison for Thursday between the flow cutting version and no cutting version. And here you can see the comparison for Friday. So basically, when cutting, we have a much higher false negative rate. So it appears that not cutting flows is beneficial for performance. We believe this is because in the no-cut scenario, normal flows have a longer average duration, so they are easier to distinguish from attacks. However, more research is needed. So finally, as a real-world example, we recently connected data from a honeypot environment with multiple protocols. And when applying an autoencoder, which is very similar to the one I described now, we get this performance shown here. I was very lucky, and I got a false negative rate of 0. So I got 0 false negatives. But the false positive rate is still high above 3%. So ideally, we want it to be very close to 0, of course, because of the problem of alert fatigue. So there's more work needed there. So we could try, for example, different or more complex models. For example, the variational autoencoder, which is a variant of the more traditional autoencoder. Or we could try ensemble learning, for example, a voting mechanism between multiple models. But in the end, such a model could be complementary to more traditional rule-based IDS filtering. So as a final note, it's important to mention the challenge of adversarial threats to machine learning-based intrusion detection systems. There already exist open source tools for this that can help us in defending and evaluating machine learning models against such threats. For example, threats like evasion, poisoning, extraction, and inference. Here I show ART as an example, which stands for the Adversarial Robustness Toolbox. And also, recent research efforts have focused on shifting from manipulations in the feature space to manipulations in the so-called problem or input space. So basically, this means modifying real objects, like, for example, packets, that correspond then to an adversarial feature vector. If you want more details on this, you can read this interesting paper, which is called Intriguing Properties of Adversarial Machine Learning Attacks in the Problem Space. So finally, some takeaways from our presentation. Do not trust third-party tools and datasets blindly, but always explore your packet captures and extracted features before applying machine learning. For real-world use, additional processing may be needed before or after the machine learning classification. And finally, beware that generating attack data with a single tool and configuration may lead to profiling the tool or the server instead of the actual attack. So here are just some additional references. And this brings us to the end of our presentation. Thank you for having us, and we're ready for your questions.